All right, so ModBus is our next wonderful topic of choice, or given, I'm going to go with it. So, quick overview of ModBus. It is another master-slave setup, all right? I looked up terms that I liked yesterday and I already forgot them, so I'm just going to stick with master-slave. I know it is horribly incorrect. I know there are better terms, more acceptable terms in the world we live in. I'm not even that old, but I'm stuck in my ways to deal with it. Sorry if I've offended anybody, but yeah. And okay, so we can have up to 247 slave devices. So DeviceNet was 63. All right, that goes back to the whole 8 bytes, 8 times 8 times 8, whatever. Anyway, 127 or 247 in this one. So a lot more. We're talking 4 times more in this one. So that's a good little bit. Just remember, this is compared to like a traditional serial connection where you only could have 2 devices. So yeah, a little give and take going on here is really what it comes down to. Yep, this is another open protocol, which means there are no royalties here, which is nice. And this is dealing with the application layer of the OSI model. All right, so we have our client-server architecture here. So we have a client and we have a server. So we have ModBus requests. All right, so the request/response type protocol and not a master-slave type protocol. So we have that option. Oh, yeah. Yeah, we'll just continue. So master requests. This message is sent out on the network by the clients to initiate a transaction. So I'm saying, hey, I need this information. That gets a confirmation back. And this is basically the client saying, I got your message. All right. Then we have ModBus indications, and that's the requested messages received on the server side. And then you have a ModBus response, which is the response messages sent by the server. So a little freaking confusing there. I'm not going to argue that statement. Now, the other confusing part about this is ModBus is in hexadecimal. All right. So we normally use a base 10 system in the US, where you have 0 through 9, right? Every spot, one single spot, is 0 through 9. There are 10 different combinations per spot, which makes life very easy, because it's like, I've counted to 10, my next space is a 1, so it's 10, it's 1, 0. And if you go to 100, it's 1, 0, 0, so, it makes sense to us. This is also what we've been dealing with for our entire lives. So that's one of the reasons why it makes sense to us. If we started with hexadecimal, it might have made more sense from us from the get-go. Maybe I should start teaching my kids hexadecimal just to screw with them. That'd be kind of fun. But anyway, hexadecimal is base 16. So not only do you have 0 through 9, you add A through F to that. So every single space, let me bring my pen up. Every single space, one little, and of course it's not going to actually draw it. Now will it draw it? Once I click this, it's probably going to show up. Hey, there we go. Every single space has, as this says, 0 through 9 and A through F. So there are 16 different possibilities per space. All right. So one single byte of information is now 0, 0 to FF. Okay. So how do we go about doing this? So if I told you that my one space, I had the letter 9, number 9 here, my single space, in decimal, that is in hexadecimal. I'm just going to put a little H underneath this so you guys know this is my hexadecimal spot. What would that be in the world of decimal? Give you a hint. It's the same. All right. So 9 is 9. All right. In the world of hexadecimal, if I had a B here, what would that be in the world of decimal? So if 9 is 9, and A there would be, B would be 11. Yeah, so B would be 11. All right, so we'd actually need 2 spaces in the world of decimal. We could get rid of this now. Let's just scrub that out. We would need 2 spaces in the world of decimal to write what that would be in 1 space in the world of hexadecimal. All right. So if this was an F, what would it be? Close, not 16, 15. All right. 9, 10, 11, 12, 13, 14, 15. So F would be 15. All right, are we all ready to mess with our minds now? All right. So what is 18 in hexadecimal and decimal? So 18 in hex, what is that in decimal world? Oh, I did this the opposite way. Damn. Nope. This 1 doesn't represent 1. Doesn't represent 10. Represents 16. So let's just take a quick look at this. When we do like a normal world of decimal and you write out the world number 15, that's like saying 10 plus 5, right? Because this is the tens. So it's 1 times 10 equals 10. And this is the world of 5, so it'd be 5 times 1, that equals 5. So we add those together, we get 15. We all with me? All right. Let me clear all this. So in the world of hexadecimal, go back. It's not the 1 in 18. This does not equal, it's not 1 times 10, it's 1 times what? 1 times 16, so that equals 16. And then it would be 8 times 1, which equals 8. So that would be 24 in decimal. That making sense? All right. So this is the ones category. So you multiply that space by 1, whatever it is. This one, you would multiply by 16. I don't know. Yeah, you keep going on and on and on. Now, there is one fun thing I like to show you guys. Here's the standard calculator built into Windows. All right. If you click the top rung and you go to programmer option, notice that we actually have the options right here. It's right now, you see a little blue line right there. That is decimal. All right. So if I type a number here, and I'm going to say, what was it, 18? X, it would be 12. All right. We went the opposite way. Let's make this 18. There you can see now decimal, we're 24. All right. If we went 100, that would be 256. So this other spot here, which would be, give me my pen back. So this spot would be 256. So it's really not bad. You take whatever the value is in the space here, right? So we put like 300 F4. You would say, well, 4 times 1 is 4. F15 times 16, I don't know that number is off the top of my head. That one's not quite in my stored. I gotta go back to a normal mode now. 15 times 16, that equals 240. And then 256 times 3, that'd be 768, I think, 768. 6 times 3, yeah, 768. And then you'd add those up, so you'd get 8 and 4 would give you a 12. 4, 6, and 1 gets you 11. 7, 8, 9, 10. Be 1, 0, 1, 2. That would be how you would do it. So it's not stupid hard. Obviously, it takes some like getting your mind wrapped around things. All right, but it's not too bad in the long run. So if I gave you AA in the world of hexadecimal, what would that be in decimal? What's the value of A? Ben? what's the value? So we have 10 and 10, right? 'Cause it's AA. 10 times 1 is? 10 times 16 is? Add them together, you get 170. All right, so it's not too bad. It's like a 3-step process to me. You write it out, then you do this where you say, okay, each spot is equal to this value. All right, this is almost like converting from binary to decimal, where it was 1, 2, 4, 8, 16, and you just go, oh, 1 times 16 is 16, 0 times 8 is 0, 1 times 4 is 4, and then you just add them all up. It's the exact same process. It's just, instead of having only 1s and 0s up here, we now can have 0 through 15. All right, that's the only real difference here. So it's not too bad in the world of long run converting hexadecimal or decimal to hex. It just takes a little thinking. Now, personally, if I were you guys, A, I'd have a calculator on my phone that could handle it really quickly if I was truly dealing with hexadecimal often. Or B, I'd have a Windows computer or something with me that, you just pop up here and you're overall good to go. That'd be my system for it. But to each their own is really what it comes down to. Long ago, I've been tired of like the default calculator app that came on my phone. I tried a few before I found this one. This is called HyperCalc. This is an Android app. I have no clue if there's a Windows app version. But what I disliked about standard calculator apps on your phone is like when you would type in next I guess I can quick show this. Let me just pull up a normal calculator because it's still on my phone. Maybe they've changed it. You do 7 times 8. Oh, they have changed it somewhat. It shows you that you type 7 times 8 in. Sometimes the calculators are just like 7, and they hit times 8, and then it just shows you 56. It doesn't like right now. It just says 56 on my screen. It doesn't show you that I did 7 times 8, right? I didn't like not being able to see what I typed in because I can't see what I typed in. I don't know if I did it. So that is why I moved to HyperCalc, because I would do 7 times 8 here. Even if I hit enter, it shows me equals 56. It shows me my original formula. I'm happier. All right. But this one, back, I can go 15 and I can do shift. And then down here, I've got binary, octadecimal, or hex. So if I hit hex and I hit the hex button, it tells me it equals F. So it will do the conversion for me right then and there. Really simple. So I highly suggest you find what you qualify as a good calculator app for your phone. The other one thing that this calculator app does, which I'm a huge fan of, I gotta go back to decimal, I guess, is I could do 15, and then I can come up here to convert, and I could say distance, and then I would say, I measured inches, and it will tell me what it is in all the different types of units that you could ever freaking want. So it's really simple when you're talking to someone, and you're like, oh, they need 15 millimeters. You're like, what's 15 millimeters? And if you don't remember that there are 25.4 millimeters per inch, you can't just do 15 divided by 25.4 in your phone. Well, I just convert and I'm good to go. So having a good calculator app on your phone is well worth the money. That one had a free version with an ad on the bottom, which pissed me off, so I did pay for it at some point. And you know what? I don't regret it. The $3 or $5 or whatever it was that the app cost me was well worth the money, because I use that app oftentimes for converting things. And it'll also do volumetrics. If you're 15 cubic inches equals how many milliliters, it would spit that number out for you as well. So very worthwhile thing to have on your phone, especially when you're in an industrial setting and you're dealing with all these weird measurements. So highly suggest it. But anyway, that is the world of hexadecimal. Now, if we go ahead and continue on, we have how it works in the long run. All right. This is overall based on serial communications, which we've spent probably way too much time on this semester, but that's okay. Serial's one's probably going to see the most often. But anyway, we have, just standard old 1s and 0s going on. Nothing too crazy there. 0s are positive, 1s are negative, just a reminder. All right. So this is really actually kind of based off RS-232, if we would look at this, because it is positive and negative. It's not TTL serial where it's just positive or 0. So you have to remember that difference, right? RS-232 was like, what, I think it was negative, it was, yeah, 25 volts, negative 25 volts, depending on which one, and like 3 volts, anything above 3 was a 0, anything below negative 3 was a 1. All right, so they're doing like the same thing here. It's have a little graph up here of 5 volts, 25 volts. I don't remember if that's the specific voltages used on this, but that's what I've got listed. So the first thing we're going to transmit, the first byte, because we have 127 different possible node addresses, that is 6 bytes or 6 bits of information, 6 or 7, 7 bits of information. Those are going to be the slave ID. The second byte is function codes, which we'll talk about in a minute. Then we have our data field, which is variable length. And then we have a CRC, which is our redundancy check to make sure we've actually got the right data, that I've transmitted the information to you and it's what I was expecting, you were expecting to receive. So here we have all the function codes. And yes, they are in a weird order. I agree. But they've grouped them to some extent. So if you notice, these first two are outputs. Oh, first three, sorry. First three are outputs, but really the first two are outputs. So it's read or write, and then this one is write multiple. That's why it's grouped up at the top, but we have a funky number to it. Then it's read inputs. That's how we have them on the screen. So then it's read inputs. And then it's analog. Analog. All right, but if we would actually look at these in normal, 1 is read, so here's 1, and then 2 would be another read, and then 3 is another read, 4 is another read. So, the first 4 are all reads, and then 5 and 6 are writes. I'm just going to put those over here. So 5 and 6 are writes. 7 and 8 are some kind of like specialty ones. And then at some point they probably said, you know what, we need to be able to read multiple or write multiple things at once, save us having to send so many messages. So that's why they added 15 and 16 that are also writes. So they are kind of grouped in 2 different ways. On my screen, they're grouped by data type. So whether it's a digital or discrete or an analog, that's how I have them up here. But they're also grouped by like, okay, we're reading, those are all together, and then we're writing, those are together. So just kind of a little bit of a give and take going on there. So talking about these 2 at the very bottom, notice I don't have any table name for them. So the loop back test, let's talk about that one first. The object of this function code is to test the operation of the communication system without affecting the memory tables at all. So basically me saying, hey, are you there? Is this working? And you're going, yeah, ball, I'm here. You got this. All right, that's all it's saying. The read exception status, however, this is a short message requesting the status of 8 digital points within the slave device. This will provide the status of 8 predefined digital points in the slave. And this could be such thing as battery, whether memory protect has been enabled, the remote input-output racks connected to the system. So it's not actually saying, what are the inputs, but it's saying like, okay, hey, we're doing this. Is your battery okay? Are you going to die on me? Type of thing. Or are we able to write to you? So that's what the read exception status is. So it's, I think I said it was 8 predefined digital points. So something to think about in the long run. Next, we have our data. So slave devices have 4 different tables, and you can see each table what they would be. So 1 to 9,999, that would be read or write. So those are output coils. So again, that's output. 1,001 or 10,001 to 19,999. Those are the input contacts. Notice that is read only. 3,000 or 30,001 to 39,999. That is our analog input. So those are read only. And then 40,001 to 49,999. That is our analog output. So those are read and write. So I find this kind of interesting. It does make perfect sense because in the world of PLCs it makes sense. But an input you can only read. You can't say, hey, make this input of this. Well, you can in the world of PLCs, you can actually do that. But basically, instantaneously, it reverts back to its old value. So it's like, hey, yeah, set that back to this. So you can't, doing it, some software will let you do it. Let me just phrase it that way. Not all software will. But even if you can do it, it basically doesn't affect anything. Same thing is happening here with ModBus. You can say, hey, what are the, give me your input values, but you can't set the input values. The output, though, you could say, what are your current output? So you could say, hey, is this output on type of thing? So you could read that information from that bank, or you could say, turn output this output on. So outputs are read-write, inputs are read-only. It does make sense in the long run. Yep. So I have an example messages down here at the bottom. All right. So a coil is a single bit. A register is up to 16 bits. So down here I have 11, 01, 0013, 0025, OE84. All right. What was the first two things again? What's this 11 stand for? Come on, I just told you that on the last page. Nobody remembers. What's the first thing? If I would say, did you turn in your thing? What would you ask me? Did you turn in your homework? If I just said that right now to the class, did you turn in your homework? We had homework. Okay, yes, that would be a good question. You'd probably be going, is he talking to me? Right? So the first thing is the ID of the device. Now remember, it's in hexadecimal. So even though it's 11, it doesn't actually mean device 11. It means device 17. So gotta keep that in your mind. All right. So let's just go ahead and pop to the next page. So here you can see slave address is 11. So that's the first one. So who am I talking to? Next thing I'm saying function code 2. If we'd go back to that whole function code thing, that would be read the input status. All right. So we're saying, hey, device 11, tell me what you've got for your inputs, and then the data addresses of the first input to read. So it's saying 00C4. Again, if we convert that from hex, that would be 196. And because we're saying read an input, it's saying, oh, that's table 10,001. So it's saying I should start at 10,001 plus 196, so the address of 10.197. And then the next number, 16, is how many coils do I want to read? I'm saying give me 16 of them, which is actually 22, because the whole world of hex, right? We're getting really confused here in the hexadecimal, I bet, because it's like 16, that means 22. You should go up to somebody and say that. You know 16 equals 22? Just see what they say. They'll probably be like, you smoking something, bud. Unless you talk to a computer programmer, and they're like, well, that's hexadecimal, bud. So, yeah, kind of an interesting one to do to someone. It's kind of like if you walk up to someone and you say, 10 equals 3. Or 2, sorry. 10 equals 2. Well, if you go to the world of binary, right? 10, right? 1 times 2 is 2. 0 times 1 is 0. So, yeah, that's 2. So, the world of binary, 10 equals 2. Or if you walk up to someone and you go, what's 1 plus 1? 10. Because the whole, again, 1 plus 1. That's okay. So we're asking for 22 coils, so that's inputs 187 to 28, and then the CRC, that's the redundancy check for error checking. All right, so this is basically saying you can somehow get like, does this equal that? And it's like, yes, it does. Okay, we're good to go. So the master device or the whatever ModBus device says, hey, give me this information, and then that goes, all right, and it says, hey, I'm Bob, right? I'm 11. Function code 2, you wanted to read my inputs. The number of bytes that you wanted was 22. You wanted 3 bytes. Now, not necessarily wanted 3 bytes, right? You said you wanted 22 inputs. Is 22 divided by 8 3? No. All right, but we have to send things in entire bytes. So even though you only wanted 22, I can't tell you wanted 22. I'm telling you, I'm sending 3 bytes of information, which is actually 24. All right. So then it says, hey, the first 8 bits are we're here. The first 4 bytes are AC, so that would be 1 byte. 10101100. The next one is 11011011. So 8, that's 16. And then we have 35, and that's because we have a 2-space holder. So it's 1028 1, so it's 00110101. So these first 2 are worthless. Like, you don't actually care about those 2. And then again, a redundancy check. So there is a lot going on there. All right, we're most of the way through ModBus. I do have a fun activity to do with this, but we're out of time for today, so that is the end of this video.